Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Ece Kilerci with us today. Hey, Ece, how you doing?
Thank you. I'm fine. How are you?
I am doing awesome on this May 19th of 2023 as we record this. And Ece, where are you located at?
I'm in Istanbul.
Istanbul. All right. Very good. We're halfway around the world on this one today. Is it summer yet in Istanbul? Or are we still in spring?
We are still in spring.
Okay.
Kind of mixture of rainy days and hot days,
And flowers? Flowers? There are lots of flowers in bloom?
Yes, we already had flowers.
Good, good. I'm in Phoenix, Arizona, and we're getting pretty warm, but the power switch hasn't been hit yet. So probably in another week or two, we will know we are in the desert in Phoenix. So very good. And Isa, what do you like to do for research?
I work on galaxies in observational astronomy.
Cool.
And I mainly work on infrared galaxies and AGN.
Nice. Nice.
These are very popular stuff right now.
Indeed. Galaxies of all sorts and all shapes, colors, and everything. Very cool. And that is going to bring us to this very awesome APJ supplement article. It's open access, people. We are in the open access era. You can go get a copy for free. Go grab one. Infrared galaxies detected by the Atacama Cosmology Telescope. And Ece, take us away.
Yes, this is a paper that I worked on for a long time, actually. This is mainly because of you really have really great referees that are really top experts in the field. So that's why we had a very good progress when we submitted the paper and get the referee report. First of all, I really want to take the referee very much, really.
Okay.
The work really improved a lot. And thank you also very much for letting us writing that long papers. And
well, thank you for writing it.
And you have the Astrophysical Journal had a very this incredible discount policy for some countries, and this was also it was great. Thank you very much.
You are welcome.
Okay.
And this is part of the product of the open access era. We do have a waiver program, people, so feel free to apply.
Yes, thank you. Yes, in this work, actually, I enjoyed it a lot because I learned a lot by working on this data. Because it was a new field for me. In astronomy, we have different, basically, we just read light and turn it to a meaningful information about what's happening in the universe.
Okay.
This is a very simple definition of astronomy. And we have different wavelengths. We have optical wavelengths, high energy like X-rays, and we have infrared wavelengths, and we have millimeter wavelengths, and we have radio wavelengths. And most of the time, one astronomer can be an expert in one of these, or maybe a couple of them.
A couple multi-wavelengths.
And that's why, yes. And when you work on objects that emit at different wavelengths at the same time, then you have to learn new stuff.
Yes.
And then this Atacama Cosmology Telescope just released a new data set.
Okay.
And their main idea to build their telescope is actually doing cosmology with it,
cool.
With millimeter wavelengths. And they have a pretty nice telescope, and because of their location, they could scan most of the southern sky.
Cool.
Okay. So, but in their data set, they also have galaxies. you can also see nearby galaxies in that wavelength, emitting in that wavelength. So one of my collaborators, actually, I have many collaborators in this work, and I also thank them, Tetsuya Hashimoto, Tomo Gotso, Ersinger, Seongjin Kim, Simon, and Valerie Wong.
Cool.
And one of my collaborators, he was actually working on some radio stuff, and came up with the idea that, I have this data set. Do you want to work on it? We had a science talk. This is how we start doing new projects.
That's
and
right.
then I was like, okay, but in case of galaxies, what is producing this light? He said, probably it is, synchrotron radiation.
Maybe.
Are you sure? I asked. He said, I don't know. You check it out. I said, okay, let me check it out. If this is always the case. Okay, because we have an idea about that, when we look at galaxies, we see that radio component from the active galaxies, for example, and as a part of this radio component, you can also see that this millimeter wavelength has a contribution in that radiation.
Yes.
Then I checked literature and wanted to see if the previous galaxy samples I worked with have any data, any emission in these wavelengths.
Okay.
So that's why I started with a large sample of galaxies. But if you want to do, if you want to search for an emission from a known galaxy, first you start with that coordinate. This position in the sky is your starting point. So where is our telescope? It's in the southern sky. So we should only get the galaxies within that map.
Yes.
Okay. So that's the first thing you do, because you just want to see if your galaxies in that region have this data. That's why we started with this sample of galaxies.
Cool.
Then we looked by position. But the other thing is very important is that you should know that your source is a galaxy. It should have a confirmed redshift.
There we go.
Okay, you should know the distance. Otherwise, astronomy is bunch of everything. So you cannot push. So that's why we started with known infrared galaxies with good redshift measurements. Then we have this map of millimeter emission at different wavelengths. It has this data from the Atacama Cosmology telescope had this 96 and 150 and 220 gigahertz maps, 3 different maps. So at each of them, we made a source matching with the coordinates from our sample of infrared galaxies. And then with the maps we have from this millimeter telescope. And most of our galaxies are confirmed infrared galaxies from 2 major infrared telescopes, space telescopes. These are Akari Space Telescope and IRAS Space Telescope. So because when you look at these galaxies, they have a bunch of radiation from stars, from their central black holes that have a huge amount of emission. And also, since they have dust inside, they have an emission in the far infrared part of the electromagnetic spectrum. So, and this far infrared radiation is really high compared to the other wavelengths. So that's why we call them as infrared galaxies. Okay. And nowadays with James Webb, they are very popular.
Yes, they are.
Okay.
Almost too
Yes.
popular, I might say, but anyway.
Yes. Uh, but we mainly call them infrared galaxies, IR galaxies, because of their far infrared radiation is too high.
Yes.
Okay.
Yep.
And usually we don't go beyond, far infrared, maybe 350 micron would
Yeah.
be something like longest from Herschel or something, some space telescope like that. But we really don't know what's, beyond that.
Right.
So the infrared part of the emission is just in between that region and the radio part that we still have a good idea about it.
Okay.
So that's why this was interesting for me. That how does this new emission that I measure go in the SCD, for example? I mean, is it part of the dust, or really is it part of the synchrotron radiation that we always assume?
Good question.
Question. That was the driving question for our paper.
Okay.
That, but of course, when you want to do something like that, it has these millimeter wavelengths. We also have, for example, a large data set from Planck collaboration. Okay, but the resolution and the quality of the Atacama telescope is a little bit better.
Okay, a little bit that one.
Yes, a little bit better. So, and we couldn't find a very large research about especially the emission properties of, very nearby galaxies.
Okay.
Because when they detect galaxies at these wavelengths, they are most interested in the dense systems that are further away. Okay, this is more interesting for most of the astronomers.
Indeed.
But yes, it is very interesting. But still, it is for, especially for galaxies, we always compare things that are more far away, with the things that are nearby.
Right.
Because for the nearby galaxies, we can study them very in detail, and we have a better understanding of what's going on them at each wavelength.
Yes.
From radio to
gamma
rays. Now we really know it, but when you go further in the universe, you lose that advantage, and you are. That's why most of the papers that people already studied, these galaxies in the millimeter wavelengths, they looked for some interesting stuff for dust lens systems, and probably our paper is one of the first very large sample of nearby studies, nearby galaxies that we investigate in millimeter wavelengths.
Yep.
So then we have this sample selection, as I really talked about a little bit, that we started with this Akari and AAS selected galaxies, but most of them are Akari selected because Akari, it was a Japanese telescope that operated for a very short time. But since it made a all sky survey, it could really detect all these infrared galaxies up to redshift 1. Because it was a 60 centimeter telescope. Yes. But still, it really made a good job. So we started with this large sample, then we checked the positional counterparts in our maps from the Atacama Cosmology telescope at these different 3 wavelengths.
Okay.
And but then we have this, for example, we have to make a measurement from the maps. So that's why we first wanted to have a flux calibration using the previous data release from the point sources.
Yes.
So in the that part of the paper, you know, for example, in this empirical flux calibration, we just say that we did this based on the previous available data release. So because they didn't release the point source catalog yet,
right?
Actually,
right.
That's why. But I think we had that was the best we could do, and the measurements are okay. So then we have this source detection, and as you can see in figure 3, for example.
Figure 3?
Yes.
Let's do figure 3.
You know, in astronomy, we usually call a source is a source if the signal's noise is greater than 5.
Then background.
It's okay.
Yeah.
Yes, compared to the background, actually it is. It should be okay. And but you know, for example, we can see that we match the PSF size of the, you know,
those are the white circles.
Catalog, yes, with the for different wavelengths,
Right.
it is different. That's why, for example, one source you see at 90 gigahertz is the same source, but their PSF is different. That's why it's when you go, from left to right, it's the same source in each panel, but they're at different wavelengths, from 90 gigahertz to 100 in the middle and 220.
Yes.
On the right hand side. So this is so here you just tell your program that, okay, this is the coordinate of my infrared galaxy, and you should go and find a source just in the middle of the this panel. Okay. So and if we find a source that the signal's noise is larger than 5, then we call it a source, a counterpart of our infrared galaxy.
Okay.
So this is how we did this source matching.
Cool.
And there's one technical part also. Sometimes you have extended sources.
Right.
And for extended sources, you should have a little bit more, I wouldn't call it complicated, but they are not easy as the point sources, because they are bigger, they are larger.
Right.
So you should define a level, a map to your extended sources. You should say, okay, if it's larger than that limit, I will call it an extended source. Okay. Then we define a limit.
All right.
About our extended source, but we made it in a systematic way so that it is consistent.
It's consistent through, right?
Yes. So and also we have a section about it in the appendix. So
there's a lovely appendix to this paper.
Yes. So it's mainly explains a little bit more in detail about how we treated the extended sources,
right? And
how we made the
growth curves.
Yes. So, for example, if you have a extended source, how much of the original PSF we call it expanded.
Got it.
For each source that looked like, and for the first, before you start doing this, you first look by your eye and you say, okay, this looks different than this one. So I should now define a way to do it systematically for my sample.
Yes.
So this is where we talk in detail about this.
Cool.
Okay.
Cool.
Yeah, you know, this is one thing that if you work with nearby sources, you always have some extended galaxies.
Yeah,
you know.
bigger. Angular size is
Yes.
bigger. Yep.
Yes.
General.
Once we have this, our counterparts, and we have this new measurements from this telescope at these different wavelengths. Then we looked at, you know, we made a sample of them. I mean, we made a list of them, like in this table, in the
let's go to
first table. Yes, yes. In table 1, we made a.
Ooh, very nice.
Yes.
And this is not the full table, people. This is just part of the table.
Yes. Yes. So we have in total like 167 galaxies. Okay. And 39 of them are detected at all these millimeter wavelengths.
Okay.
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 And so, and when we compared this our sample of these 167 galaxies with the previous samples of sample of galaxies from this Atacama telescope, we in this study we found new sources. Okay, we expanded the known infrared galaxies in this wavelength. So and we actually we had some common sources with previous studies, but 134 of our galaxies are new detections.
Cool.
In this sample.
Discovery.
So, you know, yes, in astronomy, if you detect something at a particular wavelength at the first time, this is something we do. I mean, yeah, this is kind of a discovery.
Okay.
And of course, this is good news, and that's why when we have this new measurements for these galaxies, then we wanted to understand where does it come from? Is it always a sequence from radiation? Is it dust, or is it something else?
Synchrotron.
Okay. Yes, this is very this is a very natural question that when we observe something, you first ask, where does this come from? Can we understand this? Is it, I mean, is it always like this?
Right.
Is there another way to explain? I mean, these are really simple questions, but this is what we do in astronomy. Yes. And in order to do that, to understand really the physics of the galaxy,
yes,
we need a we need to combine all the available data, you know, from a galaxy, and that's why we collected all this multi-wavelength data from literature. You know, we have this. I think somewhere I have a nice what is it, table for that, like where I get the. Anyway, somewhere I have all this summary of the wavelengths that
well, indices. Is that what you want?
Yes,
so
probably table 3. Yes,
right.
This is a summary of the all the wavelengths, all the multi-wavelength data we have. Like it is starting from
very nice
ultraviolet,
yes,
you know, to optical wavelengths, to near infrared and to infrared and far infrared.
More.
Yeah. And we have also we added some radio data from the
Really?
literature.
Very
Yes, and yeah, and when you look,
Wow.
I mean, one thing that we also explain here is that when you combine different data from different observatories, of course,
Dangerous.
you always check the quality of the data. Is it
Yes.
reliable? Because you don't want to see something at the end that a data point that jumps somewhere.
Way up here and takes the whole
Because
SED out, right?
yes, because it's not reliable, or it's already have some other effects. So that's one thing that I really did very carefully.
Okay,
That
good.
going all the details of these catalogs and checking what is meaningful, what is reliable,
Right.
to include in my SCDs.
Nice.
So that's one thing we do. And we also add this radio data to the SCDs. And then we started our, once you have all these different wavelengths on data, then you can start doing your, analysis.
Yep.
One thing that
Among
you
others.
can only do with this millimeter measurements is checking the slope of for example, you have one
Yes.
data point here and one data point here. And it's a known property of these wavelengths that you can separate in AGN emission
Okay.
from the dust
Yes.
emission just by looking at the slope.
Spectral indices.
Yes, this is what we call the spectral indices, and this is
Table 2.
in this table. Yeah, in this table, but this is just only considering this millimeter emission. This is, you have no other information here. It's just, how does the millimeter go? Is it this way? This way?
No,
That's
right.
only. And this is always, astronomers are so smart, but they have all this bunch of
Yeah.
really, this kind of very useful methods that gives you an idea about a galaxy actually. So you can make a separation about if this is an AGN dominated system, or if this is a dust star forming galaxy.
Right.
This is already what you can find in the literature. But by doing this, okay, we just separated our sample as AGN, or dust star forming galaxy.
Okay.
And we just added our newly observed galaxies, into known millimeter galaxy sample. So that's one thing we did, and we see that the spectral indices we find are, usually agree with the previous samples, and this is this is what we also expected, yes, because we work on similar galaxies. So that's one thing, and we can also see this in figure 4.
Yeah, let's go to figure 4. Let's get a visual of that table. Figure 4. Oops, that's figure 5. Sorry, my bad. Figure 4. There we go. Distributions.
Yes, this is just this spectral indices, distributions. Like you see that these, an AGN and an dust star forming galaxy, you can just separate them from the slope. But to do this is a good method, but to do this, you should have at least 2 detection.
Yeah, sure.
At 2 different bands. And we see that that's not always the case.
Fair enough.
So this limits the sample very much. if you want to only use this method.
Okay. Okay.
You see, so this is not the whole picture. So then we wanted to do the SED analysis because this is spectral energy distribution analysis. This is really where all the physics is. Because this still tells you something, even if you have just one detection at a one single millimeter wavelength.
Yes.
Okay. Yes. So that's also here you have all this information from all wavelengths, from UV to optical to infrared to radio. Okay, so so this is really combining all the photons emitted at different wavelengths from a single galaxy.
Cool.
This is, you get all the light you have, and then you just see the overall distribution from all different components. You know, what is a galaxy? Really, what do we now? You know, sometimes I give popular science. You know, sometimes I give some kind of popular science talk, and when I ask this question, now I see that kids tell me that black hole. I'm like, wow.
Okay.
Yeah, but this is kind of a new information actually. But yes, we have these supermassive black holes. They have this huge energy at all wavelengths, but on top of that, we have stars, and we have dust, and we have gas, and this supermassive black hole is really a funny place because it has also a radio emission.
Right.
So we have this radio jet. So that's why we have this radio data. But also we have this inside galaxies, we have a continuous star formation.
Yes.
So it means that evolving stars and things are going like supernova explosions. Oh, that also produces kind of wavelength at different wavelengths, emission at different wavelengths. So we are looking at this mixture of everything. Right. So that's why this SED analysis, like spectral energy distribution analysis, is a great tool to learn about galaxies.
Indeed.
And actually, in this paper, it was the perfect timing for us because we use this SIGAL program.
Yeah.
It's a really kind of a great tool to model the SEDs of infrared galaxies because it uses a physics that allows you to have an energy balance inside a galaxy. I mean, you have radiation from
everything
AGN, and you have radiation from stars, and you have dust.
Yes.
And it only allows you to produce that much far infrared radiation. So everything is in balance.
Yeah, right. Okay.
Inside modeling, when you model. So you cannot fit a point just because.
Oh, no, yeah.
Okay. But that's why it's a very advanced program now, and it's very popular now. But it has this advantage of having a reliable physics for a galaxy, So that's we call as this energy conservation between different wavelengths.
Cool.
And of course you have you account for the stars, your star formation history. You should assume something. Yes. But these are all very well-known parameters, and also well-constrained parameters. Right. But one thing that I was very happy about this latest version of this program, that in the latest version of this program, they allowed us to model the radio synchrotron radiation for star formation and for AGN separately. Yes. And that was what I was looking for.
Right. It's why you went in to learn something new, right?
Yeah, and I didn't ask for it, but when I saw it, I was like, oh my God. This is
Yay!
great.
Yay!
Yes, because actually, this is really, really cool. I mean,
Very
in
cool.
table 4, for
Table,
example, we can see, for
table 4.
example, in table 4, this looks complicated, but it's very easy. I mean, you just assume, you just put some parameters
Right.
to the program to fit your SCD. Okay, this is like you assume something from star formation, you assume something from dust properties, and you know what
Look at
kind
your
of
ISM.
dust flow should be there. Yes, how about the AGN and things like that. But then, if you look at the synchrotron radiation emission, you see it has these two different components, like from star formation and from AGN.
Alpha SF, yes.
So yes, so this
And
SF
alpha
is
AG.
star formation. I mean, so star formation of an if a synchrotron radiation can also come from star formation, but it should have this kind of parameter,
Right.
you know. So that really improved my work. I mean,
Cool.
because otherwise I would just assume one component, but
Right.
I wouldn't be sure about it. Like I couldn't claim that it is coming from only AGN, or you know, it would
Right.
be a little, you know, uncertain.
I'm with you. Yes.
Really, yes, that's why I think that's the one. Probably our paper is the first paper who made this separation, that we were able to make this separation for the synchrotron radiation.
Cool.
That since we had this millimeter wavelength, you know, and it's just in between these regions. So, for example, in figure 5, I think I have an example for it.
Oh, that's where your energy conservation comes in. Okay, got it. Mm-hmm.
Okay, so it's like for example,
Yes.
here you see an AGN, radio loud AGN, because this very brown, yes, this brown radiation
Mm-hmm.
on is lower, for example, than the AGN component, and this brown is coming from the radio star forming component.
Yeah. Okay. Okay.
For example, now for our sample, we fit these SCDs. Okay, here, for example, you see everything combined, all these wavelengths are combined, and then
Right.
we try to model this emission. And now we could really say, based on these two components, if it's the AGN that really has the contribution
Right.
for this millimeter radiation and also for the radio, or is it star forming? Because it's not always the AGN.
Right.
You see, for example, in figure 5, we see a case which is AGN.
Figure 5.
But yes,
SED for radio loud AGN. Okay.
yeah, you see on this, yes, this orange is the AGN component, and
Orange.
you know,
Yes, right here. Uh-huh.
yeah, orange is the AGN component, and this millimeter radiation, you see, and the radio is because of the AGN component.
Kind of a purpley. Oh, here we go. Right here. Yep. Mm-hmm.
Yeah,
Yep.
and that brown synchrotron is from star formation.
Cool.
So that's why we
Cool.
call this galaxy as this is radio loud AGN, and this millimeter radiation is coming from AGN. But this is not always the case. For example, if you look at the figure 6, for example, here we see, yes, this is still the AGN. AGN is still upper compared to star formation.
Right.
But for example, this is not a radio loud AGN.
Okay.
This is a radio quiet AGN.
Yes.
Okay, now we learned that, okay, we can have this radiation component both from radio loud and both from radio quiet AGN. But
Yes.
then we also see cases like figure 7. You
Okay.
see, here we see that, look at the, if we go to figure 7,
Getting there. We're waiting for the bandwidth anyway.
okay, now look at the orange one.
Yes.
It is below. So this is not AGN. This millimeter radiation
Very different.
is
So
related to the star formation.
Yeah.
Okay, and
I'm with you.
that's the first time we can make this separation based on the millimeter radiation.
Very nice. Very nice.
That was cool. And
Very cool.
you know, yes, since we could have this different model components just came in the right time, we could separate, you know, these galaxies into these 3 different groups.
Nice.
You know, because whenever we see something different, we start grouping. Yes.
Okay.
That's the general way to do.
Yeah, there we go. Yes.
So then we, for example, one thing, since we have this properties, measured physical quantities from these SEDs, like for example, in figure 9, we show some luminosity plots, for example. For example, if I measure the millimeter luminosity of a galaxy, what should be the expected infrared luminosity, for example? You know, these are really useful stuff if you want to write a proposal or something like that.
We'll take that
Or
as a
if
hint.
you want,
Okay.
and if you want to guess, okay, if I have a source at this luminosity, at this wavelength, I mean, would it be bright at the other wavelength?
Yeah.
You know, you can ask this kind of questions, and this kind of plots, like luminosity versus luminosity, would give you the answer. So for our sample, although our sample is not very large,
43.
it's still, yeah, it is still, you know,
It's not
something.
1. It's not 1.
Yes.
Not 1.
Yes,
3.
Exactly. So, and also in table 5, we just quantify these relationships. Like, what is the relationship between luminosity at 115 gigahertz if you have an AGN radio emission,
right?
Then you can find the infrared luminosity.
Very cool.
You know?
Very cool.
I mean, for a similar sample or for similar galaxies, you know, we also have the error bars, so it could work.
Nice. Cool.
And then, other than that, when you have these measurements, you have many different physical parameters of galaxies. Like you can measure the dust luminosity, how much dust there is in this galaxy, what is the total infrared radiation, total infrared luminosity, or what is the total AGN luminosity,
right?
And also what is the property of this specific AGN, how is its orientation, or you know, these are all different kinds of physics you can get from this SED.
Right.
And that's why we also have it here in table 6. And of course, these tables are very long, and we have
none of them are
these machine readable tables. Yes, and also this is a great tool. Really makes your paper tiny. And yes.
Yes, which helps the cost issue. So yes.
Yes, and for example, then one thing you can look at is you can look at the color distributions of these galaxies. For example, we show this in figure 10, for example. You know, so you have this measurements. We have these measurements. For example, we have this 90 micron measurements from Akari or IRAS. Then we have this millimeter emission. I mean, what is their ratio? Does that we ask the question, is it meaningful? I mean, can we use this only these two measurements to separate galaxies? Now, this is the basic question we have here, and we most together, you know, we see that these galaxies have different distributions, but mostly it's as we expected. Between the, for example, 98 gigahertz and 150 gigahertz, you can see that dust emission. If it's in the dust band,
Yes.
we can really separate them.
Yes.
So then it will go like this. You know, dust band is something like that.
Yeah, yeah.
So, that's kind of we can understand this, but it's. It is like we can have this star-forming galaxies, for example, have this kind of, you know, colors. This is just based on the colors. We have these distributions.
Right.
And then we checked, you know, if these colors, if they mean anything else, something like that.
Okay.
So that's why we looked at these correlations, you know. And in astronomy, correlations are very important, because when we see correlations, then we want to understand it. We are like, oh, you know, this. So that's why we kind of check different properties, but that's the only kind of moderate correlations we could claim, right? You know, with this kind of colors, you can have this kind of infrared luminosities and things like that.
Right.
And you know, with this galaxy sample, for their colors, yeah, we have similar results for the as the previous samples, but for the first time we could have this separation.
Yes.
From star formation synchrotron and the AGN synchrotron. And that, you know, that's the major contribution we have in this paper to our field.
That's beautiful. That's lovely.
Yes, and this is kind of actually important itself to see that millimeter emission can be part of star formation.
Yes.
Itself. It doesn't have to be always related to AGN. And when this is important, this is actually important if you want to select star-forming galaxies at higher redshift. So,
which is of interest.
Yes, this is actually one of the best way to study.
Be able to
study, you know, infrared radiation, or, you know, infrared part of higher galaxies, star-forming galaxies, that we select them by millimeter wavelengths.
Cool.
So our study has kind of an implication for higher redshift galaxies as well.
Yes.
And that's one thing I would really go into in the future.
We'll come to that.
Yes.
Okay.
I think that's also, like, at the very end of the paper, like in the section, you know, at section 4, we also wrote something about, you know, James Webb, but who knows? I mean, James Webb probably will observe some of our galaxies, and we can also look at their, you know, we can also put James Webb data to our galaxies. You know, probably it will be in the archives over the 5 years.
Okay.
So what would it? But it's again only about, it would have a contribution about modeling the, you know, infrared, near infrared, and mid infrared part of the SED. So, you know, maybe it can have a better constraint about the AGN
Yeah.
at that part, and the star formation at that part. Yeah, James Webb Data, everyone would love to have it. Yes. Yeah.
Somebody was saying something about a proposal, so you know.
Yes. Yes. And
I got that.
also this high redshift galaxies at redshift, for example, 2,
Okay.
we can select star-forming galaxies from millimeter wavelengths with with ALMA and telescopes like that. So deep far infrared surveys from ALMA is the future of far infrared astronomy.
Cool.
Currently, we don't have any other I don't know accepted telescopes, but
Very nice. Very nice. Asia, I want to thank you so much for walking us through your very awesome APJ supplement article. Thank you.
thank you for listening.
Absolutely. I was engaged even. I wasn't just listening. I was engaged. It was good. It's good. You touched on it a little bit toward the end there. You know, on where we go with this topic over the next couple of years. So you mentioned, you know, James Webb, you mentioned going to high redshift galaxies. Is there anything that could be done on the modeling side or on the SED fitter that you have? Are you going to be an expert in all wavelengths in about 5 years? Is there going to be a paper 2 in this series, right? So the paper 2 in this series with, you know, instead of 46, we'll have 4,060 or something like that. So
yeah, but probably one thing that we could expand this sample from other millimeter data sets. So
okay.
this was very specific to Atacama telescope data release because it was new. So it was available that time. But yes, for a larger sample, maybe from Planck and.
Okay.
But you know, I should first check the data quality and everything.
Always, yes. You made a definite point
And
about
also,
that.
yeah, and also about the modeling side, this code is getting lots of, you know, improvements over time.
Right.
So, for example, if we ask them to add a specific model or allow the models to do this, yeah, they would do it.
Cool.
So it would probably we could implement other things as well.
Software firms like that. Very cool. Very nice. All righty. Asia, thank you once again for walking us through your very lovely article.
You're welcome.
Thank you. And that will do, everyone. That will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Bye.